Welcome back, and in this video we're going to be looking at the properties of ionic compounds that arise due to the unique structure that we see from the ionic bonding model. So just a quick review of what we ended up with in the last video, this being that the structure and property of ionic substances come about due to the way we see the packing of the ions into the lattice structure. They are made up, so these compounds are made up of many positive and negative ions. So we're not talking like a single, the example that we looked at previously was like magnesium chloride, and we said that it was MgCl2. Okay, when we talk about ionic compounds, we're not talking about just one magnesium and two chlorine atoms or two chloride anions. What we talk about is that these positive and negative anions and cations, like this example of the sodium chloride here, alternate throughout a three-dimensional lattice. So just like what we saw with metallic bonding where we had a large three-dimensional array, we see the same kind of thing where we have bonding stretching off in all directions in a three-dimensional lattice with ionic bonding. But instead of having cations and delocalized electrons, we are now talking about alternating anions and cations so that they never come in contact with each other, because remember, like charges repel. So we see that the strong electrostatic forces are keeping them together because oppositely charged ions alternate throughout the lattice. Okay, so we're going to keep things of the same charge as far apart as possible. And this means that we have a strong electrostatic attraction that permeates the entire lattice. And these ionic bonds are very strong. If we look at the lattice of sodium chloride, we can see the ordered arrangements of cations and anions. Each chloride anion, and you'll notice that the chloride anion is larger than the sodium cation, okay? Each chloride is surrounded, each sodium is surrounded by 6 chlorides, okay? So this is on the surface here, and we can see we've got 1, 2, 3, 4, and then within this, if it came out, there would be another one sitting at the front here and another one behind. Okay, so they're surrounded by 6 chloride atoms, and each chloride is surrounded by 6 sodium. This means that that strong electrostatic attraction of positive and negative charge is consistently maintained throughout the entire lattice. Everyone is strongly attracted to its neighbor. This model, this ionic bonding model with alternating positive and negative charges, can be used to explain each one of the key properties of ionic compounds. These being the formation of crystalline solids, okay, the high melting points and boiling points, the fact that they don't conduct electricity when they're in a solid, they are hard and difficult to scratch, they are generally water soluble and will dissolve into ions. They will conduct electricity if we heat them up and melt them into the liquid state, or if we dissolve them into water forming an aqueous solution. And they are brittle, which means that they shatter if we hit them with a hammer or a strong force is applied. So each one of these properties can be explained according to the ionic bonding model, and you should be able to write these explanations in questions for tests and exams. So let's look at them in detail. When we look at explanations using the ionic structure, we want to first talk about the property itself and then what from that property relates back to the model. The first is crystalline solids, and we saw this with metals as well. The solid structure of the compound arises, so these crystalline structures, as a result of the repeating, highly ordered three-dimensional arrangement of the ionic lattice. So because it is three-dimensional, highly ordered and repeating, we see crystalline growth in the solid state. High melting points and boiling points. This leads to the idea that the bonding between atoms in the substance is very strong. And that makes sense because there are strong attractive forces, electrostatic forces, between oppositely charged ions that make the ionic bond very strong. The stronger the bond, the more energy is required to separate the ions, so the higher the melting point and boiling point. We look at the hard surface, okay? This means that it's difficult to scratch. So if we are putting something across the surface, the thing that we are scratching with would need to be harder than the ionic substance we're trying to scratch. Essentially, that can be linked back to the model because the ions in the lattice are held together very strongly, and it takes a lot of force to be able to make that physical change into the surface of the lattice. They're not free to move, so the lattice resists that physical change. In terms of conducting electricity, you may remember that with metals, they conducted the electricity and we said they needed to have a free moving charged particle in order to conduct electricity. Because in an ionic substance, we have these alternating positive and negative ions, these ions are not free to move. They are fixed within the lattice. Okay, there is also no delocalized electrons because the electrons are held strongly around the nucleus. So everything that is charged within the ionic substance can't move. So this means it will not conduct electricity while they're in the solid state. So if we see here, all of these charges are held strongly, attracted to each other within the ionic compound. So they have high melting points and temperatures and they're hard. Because they cannot move, they will not conduct electricity. If we think about water solubility, this will start to make a little bit more sense once we do covalent as well. But essentially what we're looking at is water is what we call a polar atom, okay? And like dissolves like. This means that water molecules have a little delta plus and delta minus. This delta means that it's a almost charge. So the water molecules have a side to them that is a little bit positive and a side to them that is a little bit negative. This means that the water molecules can ease their way in between the gaps in the ionic lattice, and the slightly positive side will orientate itself around negative ions, and the slightly negative side will orientate itself around positive ions. This forms what we call hydrated ions, and these are able to basically stay in solution, so we can see solutions of ionic compounds. And these now free the ions and they're able to be moving through solution. And if you didn't quite pick it up, that means that the ions can now move. And where the ionic substance didn't conduct electricity in the solid state, once we dissolve the ions into it, the ions can now align with the charge if we put electrodes into the solution, and they will carry the current. When we dissolve an ionic substance into water, we form what we call an electrolyte. So a solution of dissolved ions is an electrolyte. And you may have seen that term on things like Gatorade or Powerade. These are known, or hydrolyte. These electrolyte solutions have dissolved ionic compounds or salts in them to help you hydrate faster when you get dehydrated, because when you sweat or you've been doing a lot of exercise and things, you lose salts in your sweat as well as water. So those electrolyte drinks are replacing salts back into your body that you need for good functioning of your muscles and everything else as well. The other time when ions are able to move is if we melt the ionic compound and turn it into a liquid. If you remember from your particle model, liquids are able to move around. The particles aren't fixed in place. So if we melt an ionic compound and make a liquid out of it, it will also conduct electricity. The last property that we need to look at is the idea of compounds being brittle. If you think of this as a normal ionic lattice, okay, where we have alternating positive and negative charges, where the positive never comes in contact with another positive, negative never comes in contact with another negative. If we apply a force to this, it will cause one part of the lattice to shift. Okay, so if we apply a force to an ionic crystal, the lattice will shift. And unlike when we saw a force being applied to a metal, the lattice cannot adjust. We don't have delocalized electrons. So what happens now is the lattice will adjust, one part will shift down, and all of a sudden we will end up with like charges being next to each other. These will align. The repulsion between these charges will then cause the crystal to shatter. They will just push and basically smash the crystal apart. Okay, so when the lattice moves due to the force, it causes the like charges to align. That repulsion of those like charges causes the crystal to shatter. So that's it for our properties in terms of the model. Hopefully you have noted those down, and the key points to explaining one. So which part of the structure will help us to explain each one of those properties. And I'll see you in class.